Okay, here's a recap. We are doing a titration precipitation. And we've taken silver nitrate and potassium iodide and titrated them against each other. And one of these was 25, the original iodide was 25 milliliters. We added 50 milliliters of it, of the silver. And at equivalence, this equals that. All of the silver ions precipitate. But then we know that some of them will enter the KSP equilibrium and redissolve. So the amount of silver that is in solution at the equivalence point, even though General Chemistry 1 will tell you it's all gone, yes, you've removed everything from solution, but then it redissolves because it has a very small KSP. So the KSP is that number times that number, the concentration of the silver times the concentration of the iodide. Here's the KSP from the text. Those two numbers have to be the same as each other. So if those are some value x, then the KSP is this number equals x squared. X is the value of my silver ions in solution, which is the root of the KSP, which turned out to be that. Okay. And then we can get this thing PAG, which is just the negative log to the base 10 of the Ag plus concentration. And that turned out to be, what, 8.04. Okay. Now people are going to ask, what's going on in your solution? Yes, at the equivalence, but what's happening in the solution before you get to equivalence, and what's happening in solution after you've got to equivalence? Remember, we have a titration curve that looks something like this, where here is the volume of the added silver ions, and then here is this P factor for the ion that we're looking out for. And if you can do it for pH, then you can do it for any dissolved ion. Okay? There are three distinct regions. There's the region up here, there is the region right in the middle, and then there is the region past the midpoint. This is the one that everybody is interested in. That's the equivalence. And at the equivalence, the number of moles of silver is equal to the number of moles of iodide. And because they're in the same solution, in the same volume, their concentrations are the same. Here, iodide is more with silver. And here, iodide is less than silver. Okay, let's go look. Let's find a place on this curve. We've already done the straightforward M1V1 equals M2V2 from the values. I'll write the values back up on the board. That said that there was 50 milliliters of this was equal to the 25 milliliters of that at whatever the concentrations were. So that concentration has to be twice as large as this, because M1V1 equals M2V2. Okay, let's find a place where we are here. So if that volume right there, this is the volume of added silver nitrate. it doesn't matter that it's a nitrate. All the nitrate is doing is making it be soluble. The thing that's important here is it's the silver that's in solution. All right, let's find a number that is less than 50 and a number that is more than 50, and just go back through these numbers and see what we can see. So let's pick something here. What if what's happening here? So the shape of our curve is very, very, very shallow, and it's only steep close to the equivalence point, and then it shallows out again. Let's look here and then somewhere here. If we went all the way out here, we would see the same thing, but so we can go maybe a little bit out there. Okay. So we started at equivalence. Let's look at a different case that is before equivalence. Questions so far? I think that equivalence is the easiest part. Doing this at volumes that are not at equivalence means that we have to find what's the leftover bit, or the unreacted bit, what's in excess, and then take a look at that. Okay. Let me restate the question so we know where these numbers come from. We had 25 milliliters of 0.1 molar potassium iodide titrated against 50 milliliters of 0.05 molar silver nitrate. There you go. So because M1V1 equals M2V2, because that concentration is twice as large as this concentration, that means this volume has to be twice as large as that volume. Okay? All right. Let's look at the case before we get to equivalence. Let's look at after I need to add 50 milliliters of silver to remove all the iodide from solution precipitated as silver iodide. What's going on in my solution at the point when I've only added 10 milliliters of silver nitrate? Okay. There's more iodide in solution than there is silver. Okay. So all of these silvers are surrounded by iodides. They have no trouble finding iodides. So all the silver ions added will precipitate. And they will take iodides with them. So the amount of iodide that has been removed is the same as the amount of silver that has been added. All right. The moles of iodide equals the moles of iodide. Oh, yeah. This is not mole. These are not concentrations. Anything that is to a 0 is your initial amount. This is the amount of iodide that is remaining. The added silver removes some iodide. The same number of iodide as you have used. So the moles of iodide is equal to the moles of iodide that you started with. And we're going to subtract from it the number of moles of silver that we've added.
I have a quick question, Dr. Moore. So how do you like reason to know that all the silver added will precipitate? Like why will
Because the KSP for silver iodide is 10 to the negative 17. So it's really, really insoluble. So, and one of those things, when, here's a reactant A. If it is surrounded by inert material, and it has to swim through that inert material to get to reactant B in order to make the reaction. So when A and B combine, they make these circles. These are the products, right? So A never reacts with the product. A only reacts with B. So when we have low concentrations and low availability, these have a hard time meeting each other. But when one of the reactants significantly outnumbers the other one, these have no trouble meeting at all and turning into product. And right now, I have a lot more iodide than I have silver. And I know that when silver meets iodide, it makes something deeply insoluble. So it will precipitate. It's just outnumbered. Okay. What do we know? Molarity is moles per liter. Therefore, moles is molarities times liters. Okay, so I can find the number of moles of the iodide. That's in the initial. Have to be liters. I have 25 milliliters of potassium iodide, 25 milliliters. There are 1,000 milliliters in a liter, and I'm going to multiply it by its concentration. That's the number of moles of iodide. And I'm going to subtract from that the number of moles of silver nitrate, which is 10 milliliters. Same conversion factor. Got to turn that into liters by dividing it by 1,000. And it is 0.05. want to do it along with me or just trust me?
I trust you.
Mm,
I like slightly smaller.
some of the time it works out. When I add 10 milliliters of silver nitrate to the 25 milliliters of potassium iodide, the silver reacts with however many moles of iodide it is equal to, and then that gives me this. This is my moles of iodide that are still left over. That's the moles of iodide remaining. Okay, let's look at what have we done to the solution. The volume of the solution is the 25 milliliters that we started with, that came from the potassium iodide, and then an additional 10 milliliters that came from the silver nitrate. Okay, so that is 35 milliliters, which is 0.035 liters. The concentration of iodide is the moles of iodide divided by the liters of solution .002 moles divided by 0.035 liters. That is 0.05714 moles per liter. Now, how much silver is in solution?
It's precipitated.
It did, it all precipitated. And then what happens?
Goes a little bit back.
And then it redissolves. Just a tiny bit. How much? So all of the silver ions have precipitated. And they have to, because the concentration of iodide is larger than the concentration of the silver. They're outgunned, they will precipitate. Okay? But they follow, now that it's precipitated, the rule says some of it will come back. And the KSP for this is the concentration of the silver multiplied by the concentration of the iodide, and the value for KSP for silver iodide was a big number. I say big number, tiny number. 1.45 times 10 to the negative 15. the values. Before did I just, no, it's up there. Okay. That number times that number is equal to this number. AG plus is the number I'm trying to find. I minus, it's on the board. Oh, wait a minute. Wait a minute. I wrote the wrong number down. Yeah.
Okay.
Yeah.
I was like,
Yeah, I actually said out loud a few minutes ago that it was 10 to the negative 17. That number is the final number. This is 8.3 times 10 to the negative 17. That number right there. 8.3 times 10 to the negative 17. The KSP for silver iodide is 8.3 times 10 to the negative 17. When you divide 8.3 times 10 to the negative 17 by 0.5714, you get that number that I accidentally put on the board. That is 1.45 times 10 to the negative 15. Yeah. Okay. Still a very, very small number. Okay. Your PAG is the negative log to the base 10 of your AG concentration. And PAG equals you don't have a calculator.
14.
Not really sure I'm allowed to have 4 digits of precision. Oh, actually, you know what? Well, I don't know about that number. Did that one, if that one came with the second one. So, what have we got? What was the PAG at equivalence? We just had it on the board.
8.04.
8.04. At equivalence, PAG is 8. Before equivalence, PAG is 14.8. Let's go look here. Let's go past a bit and see. This is a very shallow part of the curve. This is a very shallow part of the curve. Making changes in volume here don't have very much effect. Making changes in volume here might. Let's go look there. Okay. Now, I said last week that there is an alternate way of doing this, and I'm not particularly comfortable with it. The alternate calculation goes this way. That the iodide concentration is equal to the fraction remaining. Doesn't have to be the fraction remaining, just has to be a fraction. Because later on, when we go past, it's surplus. Okay. Multiplied by the original concentration, multiplied by the dilution factor. Okay. Let's look at this. The volume at equivalence. Volume, capital V, equivalence, was 50 milliliters. We learned that M1V1 equals M2V2. The volume added is 10 milliliters, which means the volume still to go is 40 milliliters. So the fraction remaining is 40 milliliters over 50 milliliters. Our original concentration, right here, was 0.1 volts per liter. 0.1 volts per liter. And the dilution factor, this guy, your original volume, for the iodide is 25 milliliters. Your total volume is 25 plus the 10, which is 35 milliliters. So your dilution factor here is 25 milliliters divided by 35 milliliters. All of those numbers put together find the value of iodide, which comes out at 0.0571. You still have to go find the value of silver by doing the KSP. I think if you did this lots and lots of times, and you were familiar with this, this might be useful. I only revisit this once every other year, so this is not in my repertoire. All right. Let's go past equivalence. So we have three cases: at equivalence, before equivalence. Here's the third: past equivalence. Let's go just a couple of milliliters over. If I add 52 milliliters instead of 50, I am 2 milliliters past equivalence. Do people still say IE?
Yes.
Okay.
At least my textbooks.
Okay. I don't know, some things, example, right? And exemplar gratis, it's Latin.
Oh,
It est, it's Latin, it is.
oh, I was wondering where
Yeah.
they were coming from.
The other one, QED. When you prove something, you say QED, quod erat demonstrandum. It has been shown. Yeah. This is the one that's got me annoyed because that has been around for a really, really long time. And people have started saying EX, which already means excluding. So you write, here's something, EX, and the rest of the world reads, here's something, but not including any of what I'm about to say. Yeah. Mm. All right. Let's look for the moles of silver, which is equal to the molarity of the silver times the liters of the silver. All right, we're past equivalence now. So the number that we're going to use here is that first 50 cancels all the iodide out. It's gone. Precipitated. This is excess. I have 2 milliliters of silver in solution, giving me silver ions into solution. So the moles of silver is this. And this is the moles of silver that are in excess. Concentration of the silver is the moles of the silver divided by the liters of the solution. Do I have 3 zeros? Yes. How much solution do I have?
52
Plus,
25.
I have my original 25 milliliters from the potassium iodide, plus I now have 52 milliliters from the silver nitrate. Those are in milliliters. So, we're gonna divide all of those by 1,000 to get them to be in liters. Okay.
This is a dumb question, Dr. McGuire.
Yep.
But where does the potassium go?
Do you remember we said that things were spectator ions? They are until the next chapter.
Okay.
they will remain the potassium. So what happens is that potassium meets that nitrate. It makes potassium nitrate. All group 1 salts are soluble, all nitrates are soluble. This is quite happy just being dissociated ions in solution. Swimming around, not getting in anybody's way, not contributing to something called the ionic strength of the solution at all. And they will remain that way for maybe like 5 more pages in the textbook.
Perfect.
Yes. And then we have to say, is it possible that that ion interferes with this solubility? Yeah. Yes, it does. Yeah. Yeah. It's a progressive screw that turns and tightens, and the pain is progressively. We don't do it all in one twist because that would be it's just slow enough that you can sit there and say, I can take this another week.
Another week.
Another week.
One more week.
Just one more.
One more. Your wall being shattered really quicker than mine was. Mine was shattered maybe last year. This is a lie. That's a lie.
All right. At 72 milliliters. 0.0001000, lots of zeros. Moles, 72 milliliters. That's 100. That's 100 milliliters. There you go. Up. There you go. 77. So the silver concentration turns out to be 1.3 times 10 to the negative 3. Okay. Now, what's the PAG? Yeah. So 2.89. Puts us all the way down here. And we've seen that when we've plotted titration curves before, that everything is bunched and then there's this rapid change and then it all bunches back together again. This is the part of the curve where small changes, and a 2 milliliter change is not small. You know, a drop. We did a titration in chemistry 1 again last week, phenol phthalein. You get the nice pink endpoint for your titration. 1 drop, it goes that hot pink that you were way, way past the equivalence point. Okay. What's missing from this calculation? What have we not done this time around?
We did not talk about I at all. Ion.
We didn't incorporate KSP, right? Why not?
Is it too large?
Because KSP is really, really small. And you've just drowned it out. Now, this is real, the silver plus that's in solution, in excess. So if we were to factor in the value of KSP was 10 to the 8.3 times 10 to the negative 17. not with not with two significant figures, you know. Yeah. It's way the amount of silver that is either being added or subtracted from this number is minuscule. Okay, so once you go past equivalence, we don't need to count it. All right. Now, what's next is, what if there's more than one thing? What if there's more than one thing in solution? Oh, how about this? Just thought of this. What about this? I just erased it. Here's our titration curve. And this is for PAG versus the volume of AG. Really, that's for the +1 ion. This is for AG plus versus iodide. Is it exactly the same graph for every concentration of iodide? No. No. What if I diluted the iodide? What would the shape? What would that do to the shape?
It would shrink it. Less ink in the middle.
Would it change the number of moles of iodide being equal to the number of moles of iodide? Did I just say the iodide twice? Would it change, if I change the concentration of the iodide solution that I'm titrating the silver against, would that change the fact that equivalence happens when the moles of silver is equal to the moles of iodide? No. So that central point is shared on all of the graphs. Not this way.
No?
That way.
Oh, because the amount of the concentration of the iodide is
Yeah, that makes sense.
If I dilute it, it's just, I don't have as much of a spread. Okay. We know that number. 8.3 times 10 to the negative 17. What do you think the plot of AGBL looks like? expecting you to know the answer. I guess.
It's definitely gonna be smaller somehow.
Yeah.
I don't know if it's like gonna.
Okay. This represents the part where there's more iodine than silver. Here's my equivalence, and here is, I'm adding silver, and it's doing me no good. Just that. I don't have a third color.
You need more talking about?
Oh, yeah. As long as it's not purple.
It's nice purple though.
We see this. They stack in terms of the KSPs, and the equivalents is are at different points. They're at different points because this one takes out all the iodide, precipitates, and then only puts back a tiny amount of Ag+. This one precipitates everything and then puts back more. So their equivalence not at the same place. The equivalence is halfway down the steep part. Not the same. I'm not the only one hearing that.
Yeah, it's, I don't know, it's almost like a triggered alarm.
Oh, she's got
Are you kidding me? That thing shouting at you right now is the air conditioner? That's so weird, I thought an alarm was going.
Okay. Let's put all of that together. Am I gonna go KCl? Yeah. Let's put these far apart from each other. I've got potassium iodide and potassium chloride in solution. Add silver nitrate by titration. Okay, so nice and slowly. There is a chance that if you do this really quickly, you trap some of the other ions in the precipitate. Okay, so if I'm silver and I really make an insoluble solid with iodide, and you give me lots of iodide all at once, but you also give me lots of chloride all at once, then I just grab what's available, I precipitate, and that solid will have trapped chloride in it. So when you're doing this for real, stir that solution, agitate it, and add this slowly. That gives everything the best chance of making a choice. Which one of these is going to be the least soluble? smallest KSP is the least soluble. How much more soluble is silver chloride than silver iodide?
10 million.
10 million. It's 10 million times. So if you do this nice and slowly, you get what you expecting. If you do this rapidly, you're going to trap something else. Okay. Now, who's had biochemistry?
Oh boy.
pH titration curves of amino acids. What do they look like? Double bumps.
Oh, I do remember.
They have more than one bump. Because every amino acid has the acidic end and it has the amine end, which is a base, and they have side groups, and those side groups are polar. They could be acidic or basic. So I could have 3 bumps in a titration curve for an amino acid. Not sure that that's a chapter in our book, but it probably should be. So the first thing that I will see is what's going on here is that both the concentration of iodide and the concentration of chloride are much, much larger than the concentration of the silver. But it's not the chloride that is making this happen. It's the iodide that's controlling the concentration of the silver. Because the iodide has the lower KSP. Okay? So this will go, and then it will stop. Now these are they're never flat. They always have a little bit of a curve to them. That's a bit of a downward curve, and then a bit of a downward curve here, and then it does it again. That might be exaggerated. That's too much added volume. Mind you, it is 10 million times different. Okay. The equivalence for the second is halfway down the second curve. This one's a little bit different. What we need to do is eradicate the curve right here and just find that, extrapolate that as a straight line, extrapolate that as a straight line, and right here. So VE is the volume at equivalence. That's the volume at equivalence for the chloride ion. And this is the volume at equivalence for the iodide. Got a couple of calculations to do about mixtures. I think that can wait. There's a nice little trick that I read in the book. Actually, the way that they describe it in the book is much, much more complicated, but there is a nice little trick of, if you're doing a silver, so silver is a really good way of precipitating halides, because they're all very insoluble, and as you go down the group, they become really insoluble. So we would use a silver nitrate titration to find that number. And there's a really cool trick. Let's erase this. Because we have no acid-base indicator, right? We have nothing telling us that there's a color, there's no color change anywhere here to tell us what's going on. So there's a trick. Thiocyanate anion. So we would make a really, really intense red color with iron. And we use that in chemistry 2 lab twice to make a red color with iron. Once in the colorimetric analysis and once in the spot tests that first week where we did all the test tubes, put them in the centrifuge, and did the precipitations one after the other. And you add potassium thiocyanate, and if it goes red, you have iron in your solution. Well, silver thiocyanate has a KSP. I had to look it up. Oh, 1 times 10 to the 12. Negative 12. Okay. So what we do is we add iron to the mixture that we want to find the concentration of the silver of. Right. And then we add the thiocyanate. And this makes insoluble silver thiocyanate. And we wait until the very, very last atom of silver is precipitated. Then the iron and the thiocyanate get together and they make the solution go red. So we can test with really good confidence what the concentration of our silver is by this. And then when we know the concentration of our silver solution, then we can titrate that against an unknown amount of iodide or chloride or whatever. So this is not always the answer. This is oftentimes the first step that we have to do to standardize solutions so that the next step is done. Okay? A couple of calculations Thursday about mixtures. We're at the point where I can release an exam to you to do, because we've got plenty of material now. We'll have that run for a week or two. the exam. Be open for a week. Yes?
So it's online?
Yeah, I'll